Okay, so welcome to lecture 11. Today we're going to finish up chapter 4 and start a little bit on chapter 5. As I said, next week will be the last week. Next week we'll finish up chapter 5 and then do a little bit on chapter 8, which is the clustering chapter. Okay, so let's see. This is a homework assignment, which you don't care too much about. So chapter 4 is titled Classification, Basic Concepts, Decision Trees, and Model Evaluation. So again, the point of chapter 4 was basically to introduce you to the classification problem. We talk specifically about decision trees, which is one method for doing classification, just so we have at least one example. And sort of historically, this is one of the first methods that people dealt with. Now, of course, we have more modern techniques that are much more effective, which we'll talk about in chapter 5. And then we'll talk about sort of how do we evaluate classification models. So this was sort of the picture of the problem, right? You have data, and there's one attribute in particular that you care about. You want to be able to predict that one attribute as a function of the other attributes, and that attribute is a binary attribute, which makes it a two-class problem. Here it's called yes or no. We could generalize to having multiple classes, but we're not going to generalize to it having to be numeric, because then that would get into a regression problem. So we're trying to predict a binary outcome here using, in this case, three attributes. So we learn a model, which is the induction process. Then you take that model and you apply it to new data, and you want to see how well you can predict the class correctly on new data. Now, in order to have some measurement of how well you're going to do, because when you get new data, you're not going to know the class, so you're not going to know whether you're right or wrong, but you want it to perform well. So to have some measurement of the performance, you hold out some of your data as a test set, pretend like you don't know the class, pretend that that's new data, use your predictive model, apply it to the new data, get the class estimates, and then see how close those are to the actual estimates. And that would give you an estimate of your generalization error or your misclassification error on your test set. So that's a picture of the problem. The description is here, right? So we have the training set, which we call the attributes X, and then the additional attribute Y is the one we're trying to predict. And we use a model to predict the class as a function of the other attributes. And the goal, again, is that previously unseen records, right? If I get new observations, I ought to be able to predict the class as accurately as possible. And again, a test set is used to determine the accuracy of the model. Usually the data set is divided into training and test sets, with the training set used to build the model, and the test set is used to validate it. Of course, you know, so there's more advanced procedures like cross-validation, where you repeatedly leave out different fractions and use those as test sets, and a number of other procedures. There are many techniques, algorithms for carrying out classification. In chapter 4, again, they're focusing only on decision trees. Chapter 5 gets into more modern and effective techniques. And that is sort of to say that decision trees are neither modern nor effective, which is a pretty accurate statement. Although someone asked me last time, they said, but we use decision trees when we do boosting, or we use decision trees when we do random forest. Yes, okay, that's true. Decision trees are often used in some of the other modern and effective techniques, but by themselves, they sort of come out of favor in favor of some of these other techniques. Example of a decision tree we saw last time, this for trying to use whether or not someone got a refund, whether or not they're married, single, or divorced, and their taxable income to predict whether or not they cheat on their taxes. So this would be an example. Of course, when you apply it to new data, you're not going to know whether or not you're right or wrong, but if you apply it retrospectively, you can use some data to fit it, and then a new data set to predict and see how well you're doing and measure your accuracy, so you can determine how accurate of a predictor you have built. Most algorithms that grow decision trees use sort of a top-down approach. So you start off with dt in any node, and if all those belong to the same class, that's a terminal node, and you stop. If they belong to different classes, then you continue to split. So you sort of start at the top, and then you keep splitting as you go down. So usually the splitting is done in a greedy fashion. Greedy means that you simply choose the optimal split at each stage according to some criterion. Now, that may not be optimal, even according to the same criterion, because you're not looking ahead, right? You're only doing what's locally optimal. However, the greedy approach is computationally efficient, so it's popular. And then we just mentioned last time that we had sort of three questions to ask, right? What types of splits should we allow? How do we select the best split? And when do we stop? Well, for number one, we said let's just use binary splits to be consistent with what the R-part algorithm is doing. So nominal attributes, you split sort of all the classes, some of the classes on one side and the rest of the classes on the other. Ordinal, you might want to preserve the order, although R-part doesn't bother with that. And then numeric attributes, you basically choose a cut point. Everything less than that cut point goes on one side. Everything greater than that cut point goes on the other side. For number two, what type of criteria should we use? Well, we can either use misclassification error, Gini index, or entropy. I mean, you could imagine other criteria too. All of these are within a node, sorry, not a terminal node, within any node that would be a terminal node if you stop there. Within any node, how pure is it, okay? And in reality, this is like the lack of purity, right? So if I have one of the classes is 70% probability, then 1 minus 0.7 is 30% misclassification error. So 30% is a measure of how impure it is, okay? Gini index and entropy we'll talk about too. All these measure the lack of purity or the impurity within a node. In fact, entropy, it's intuitive, right? How much entropy is there? The maximum of all these, of course, would occur when you're at 50-50 for the two-class problem. Okay, so why would we use misclassification error to determine the splitting on the nodes? Well, we care about misclassification error, right? In the end of the day, you want to know how low your misclassification error is on your test set, so it might make sense to use it as the splitting criteria. The reason we don't often use it is because it's sort of discontinuous, and I'll give you a nice example of that in a second. But it's a simple thing to use. 1 minus misclassification error is called the accuracy. And then we left off with this example last time where we said, suppose that this is the data. I have 3 attributes, A, B, or C. They're all either true or false. And then the question said, well, which attribute should I split on? And actually, we figured out that you should split on A, right? Because initially, your misclassification error is 50%, right? You have 50 positives and 50 negatives. So initially, it's a 50-50 case. So you have misclassification error at 50%. However, if you split on A, you can see that the positives for A, let's see, where A is true, so this is A true, and this is A false. If you look at just the examples with A true, you see there's 25 here, 25 positives, and 0 negatives for A true, where when A is false, you see 25, 50 negatives, and 25 positives. So 25 positives and 50 negatives. So splitting on A, true or false, in one node, you could call this the positive node because it's 25 positives and no negatives. And the other node, you could call this the negative node because there's 50 negatives and 25 positives. And you see that you have one pure node and one node that's sort of 50 out of 75 pure. And so you're only going to classify 25 of the 100 observations wrong. So the misclassification error for this tree is now gone from 50% to 25%. And that is a better split than B or C if you check them out. Now, the reason I sort of brought this up again is because if you look at those 3 measures, right, they're all measures within a node, right? They're all measures within a node, all these 3. And so the question is, if you have a measure within a node, how do you combine them to get the overall measure? Well, let's just take, for example, this one, right? Misclassification error is 1 minus the maximum probability within the node. So here, you have 2 probabilities, right? 100% and 0%. So the maximum is 100%, so the misclassification error in this node is 1 minus 1 or 0, right? This node has 0 misclassification error. The other node, you have 2 probabilities. You have a 25 out of 75 and a 50 out of 75. So 50 out of 75 is the max. So misclassification error is 1 minus 50 out of 75. So the misclassification error in this node is 25 out of 75. So I have 2 nodes. One has misclassification error 0. One has misclassification error 25 out of 75. So how do you combine them to get the overall misclassification error? Well, you take the weighted average, right? 25 of the 100 are in that node, which has misclassification error 0. And then 75 out of the 100 are in the other node, which has the misclassification error of 25 out of 75. And so, of course, obviously, right, you wind up with 25 out of 100, which you knew, because you said, well, you're just getting 25 of them wrong. The reason I just went through this, though, is because in general, that's how you're going to combine these metrics, right? You compute them within each node, and then you take the weighted average over all the nodes, okay? So it's obvious for misclassification error, but in general, for Gini index, we'll compute Gini index within each node and then take the weighted average to figure out the overall Gini index. Same thing with entropy. So that's misclassification error. We did this example. Gini index. Okay, this is actually what gets used in our part, in R. Why does it get used in our part in R? Because our part in R is based on the CART algorithm, which suggests you should use the Gini index. For 2 classes, you can see Gini index actually turns out to be proportional to the binomial variance. After you compute it in each node, again, you take the weighted average, right? Weighted average within each node is the overall Gini index. So you compute Gini within each node, and you take the weighted average. So let's see. Here you can just see node-wise computations. Of course, this would be a completely pure node, right? 0 is 6. So you take 1 minus 0 squared minus 1 squared, you get 0, right? So Gini is measuring sort of the lack of purity. So it's 0 here, because this is completely pure. And then, of course, Gini will increase as you get closer and closer to 50%, okay, because it's simply measuring the lack of purity. So, of course, the highest one would be if I had 3 of each, which isn't up here, but you see it increasing. And again, you just take all the probabilities, you square them, and then you subtract from 1 after you add them up. Okay, so this is the example. I don't know if I'll sort of go through this one the full way just to save time, but this is one of the problems out of the textbook where they basically ask you, should you split on A1 or A2 according to the Gini index? Maybe I'll just do one of them. Of course, you have to compare both of them and then say which one is better. Again, you're going to compute the Gini index within each node, and then you are going to take the weighted average across the 2 nodes to figure out the overall Gini index. So let me just do A1. And so suppose you split on A1. I guess it's, again, either true or false. If I split on A1 true or false, well, let's see. A1 true, I have 1, 2, 3 positives. Tell me if I count these wrong. And A1 true, I have 1, that's it, 1 negative. So then A1 false, I have only 1 positive. And so A1 false, I have 1, 2, 3, 4 negatives. Is that right? That means there's 9 things here. Okay, 9 things, good. Okay, so 3 to 1 versus 3 to 1 and 1 and 4 to 1 on the other. So sort of both nodes are almost pure, right? This one has sort of 25% and 75, and this one has 20 and 80. So both nodes are almost pure. So then how do you do the Gini index? Well, for this node here, right, you're just going to take 1 minus 0.25 squared minus 0.75 squared. Okay, and then for this node here, you're going to take it as 1 minus 0.2 squared minus 0.8 squared, okay, and figure out each one of those. And so then the overall value, right, is going to be the weighted average of these. So let me just sort of write the overall value. So 4/10 of the observations are here, right? So you're going to have 4/10 here. Sorry, I always think there's 10. Thanks. 4/9 here for whatever this first value is, plus then the 5/9 here for whatever that value is. Okay, so I can just sort of do that in R in one shot. And let me do that and then check it with the number on my paper to make sure it's right. I think the only thing you can mess up is the signs in this one. Let me see if I can make this a little bit bigger. GUI, let's do 14. Okay, there we go, that looks bigger. Of course, I can't see my cursor. Okay, so what did I say? So 4/9 times that node plus 5/9 times the other node, and then the first node we had probabilities of 0.25 and 0.75, so 1 minus 0.25 squared minus 0.75 squared. And then the other node was 0.2 and 0.8, right? 1 minus 0.2 squared minus 0.8 squared. That, there's some funny parenthesis there. There's too many parentheses. 0.2 squared minus 0.8 squared. That looks right. So 0.344. Let's see if that's the right answer. It sounds familiar. Gini index for this one is 0.344. Yep. And it turns out, so A1 gives me 0.344. 0.344. If I split on A2, I'm not going to do that one just to save time, but if I split on A2, turns out I get 0.489. A2 is not such a good split. So that would favor splitting on A1 in that problem. So that's just sort of one of the textbook problems that tells you if you were to start with the decision tree and finding your first split, and you were using the Gini index, as our part does, it would split on A1 right away. And so decision trees, the one nice thing about them is that they sort of have this sort of built-in variable selection, right? They sort of consider all the variables, which, sort of might all be correlated and might all do a good job, but they sort of pick out, at this stage, which is the best one to use, and once they pick it out, they also tell you what is the best split to use. So not just saying, here I have to split true or false, it only has 2 values, but they find the best split, and they tell you which variable to use. So there's some nice features about them which we'll exploit later when we use things like boosting and random forests. Okay, any questions about that problem? Okay, so that's sort of what our part is doing internally when it starts growing the tree from the top down. Now the one thing we wanted to talk about is why would you use something like the Gini index to grow the tree when you really care about misclassification error? Well, I think this example is sort of one of the simplest examples that can show you why that might be useful. Again, the the Gini index sort of has like a nice gradient where it kind of points you in the right direction with regard to the probabilities, whereas misclassification error really throws out the probability information and is sort of discontinuous and only looks at how many are right or wrong. So if you take this example, for instance, you start out with a parent node that's 7 to 3, right? So you have 7 C1 and 3 C2. So initially, your misclassification error is 30%. Okay. And so then you're going to split that. Suppose you had one attribute that you were considering splitting on, attribute A. It could either be yes or no. Okay. And when you split on that, node 1 becomes 3, 0, and node 2 becomes 4, 3. Now, the interesting thing is, right, if you were to pick the majority class in each, well, first, let me do the Gini index, right? So Gini index for 3, 0 is 0, right? Because that's a pure node. 1 minus 0, 0, right? So that's a pure node. Gini index for this one, 4 and 3, well, 1 minus 4, 7 squared minus 3, 7 squared, 0.490. It's pretty big. In fact, it's bigger than the parent node, but when you take the weighted average, 3/10 are in here with 0, 7/10 are in here with 0.49. It actually comes out smaller, right? So Gini index says, you know, this is actually a good split to do. Decreases the Gini index. I mean, you can compare it to other possible splits, but, you know, this one gives you a decrease from 0.42 to 0.343. However, if you were splitting only on misclassification error, as we did last time, you would see this node would be called class 1, and this node would also be called class 1, and so you're still going to get those 3 wrong. So your misclassification error would start at 30%, and it would stay at 30%, and so Gini index doesn't really point you in the direction of this split. It doesn't really tell you that this split is any better than what you started with. So misclassification error tells you that this split is just as good as the original split. It doesn't tell you that it's any better. Whereas the Gini index goes down from 0.42 to 0.43. The misclassification error stays at 30%. So this is why we often want to use some sort of surrogate loss function, such as the Gini index. Even though in the end of the day you care about misclassification error, the Gini index is nice because it sort of carries along information with you to sort of help you grow the tree. Just like when you do logistic regression, right? You do maximum likelihood. Even though you care about misclassification error in the end of the day, still the likelihood function gives you some extra information and turns out to be optimal to use that. Same thing with the Gini index when you grow the tree. Even though you only care about misclassification error at the end of the day, the Gini index will sort of point you in a good direction because it will use the extra information from the probabilities. Okay, any questions about that slide? Okay, so then the last thing we had to talk about is entropy. Entropy, similar to Gini index, right? I mean, it might suggest different splits, but just like Gini index, it's going to use the information, the probabilities, to sort of help you grow the tree. So how do you compute entropy? Well, p times log p, negative, and you sum those up. Log base 2, just to be specific, there's, of course, theoretical reasons for why log base 2, and we can talk about those. You can motivate it a lot of different ways, but entropy has a lot of nice interpretations that you can come at from different angles. Similar to, it's used in C4-5, right? So if CART and RPART use Gini index, then C4-5 uses entropy, which is one of the differences between those algorithms. Probably not the biggest difference, but it's there. After you compute the entropy in each node, again, you take the overall weighted average. The decrease in entropy has a special name. It's called the information gain, right? So if it's just, you know, when you're using Gini index, you just look at the decrease in the Gini index. When you look at the decrease in the entropy, that's called information gain, just sort of a special name, and they talk about that on page 116. So it's sort of similar to Gini index in that it's a measure of purity, or rather impurity, and then you take the weighted average to determine how to do the split. Here, of course, you see, so you say, well, why is this 0? Well, we're going to define 0 log 0 to be 0, just because, you know, the limit as x goes to 0 of 0 times log x is, of course, 0. So we define that to be 0, so then you get the answer you want. The perfectly pure node has 0 entropy. Okay, that's, of course, what you would want. And then 1/5, 1 and 5 has 0.65 entropy. 2 and 4 has even bigger entropy, and of course 3 and 3 would have entropy 1, which is the largest entropy you're going to get. So that's how you compute entropy within each node. Similar to Gini index, it sort of starts off at 0, then increases as you get to the 50-50 case. So here's a problem from the textbook. It says, for the following data set for a binary class problem, calculate the information gain when splitting on A and B. Which attribute would the decision algorithm choose? So maybe I will run through this one depending on how much time there is. The first thing, though, you have to know is when it says calculate the information gain, they're not just saying choose which attribute is better. They specifically want to know what the information gain is. So the first thing you're going to have to do is compute the original entropy of the tree before you do any split. So this is number 38. So you would say entropy for the original tree is something like, well, the original tree has, now, is it 9 or 10? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 this time. 10 things, 4 of which are plus. So it would be like negative 4/10 log of 4/10 minus 6/10 log of 6/10, right? That would be the original entropy. And of course, this is log base 2, which, is just going to be a scaling. But to be specific, we should do that. So let's see. Negative 4/10 times log of 4/10. Now, of course, r is not using log base 2, so I'll just divide by log of 2 minus 6/10 times log of 6/10 divide by log of 2. And that looks right. 0.97, let's call it 0.9710. So that's the entropy for the original data, right, before you do any splits at all. And so when you're computing information gain, you're going to take the difference in entropy between the split and this original value of 0.9710. So let me just do the, I'll do the split on A just to see. I won't do the split on B. So suppose you were to split on A, and A can either be true or false again. Now again, these are all simple examples because there's only one. Once you say I'm going to split on A, it's either true or false. But again, A, if it were numeric, you'd have to look at every possible split. If it had multiple categories, you'd have to look at every possible way of putting the two categories into two groups. In this case, if A is true, I get 1, 2, 3, 4 pluses. And if A is true, I get 1, 2, 3 negatives. Okay, so that's a pretty heterogeneous node. If A is false, I get 1, 2, 3 negatives and nothing else. So that's a perfectly homogeneous node. Oops, I should say positive 0, not, yeah, positive 0. Okay, so there we go. That's sort of the story for A. And again, how are you going to do this? Well, you're going to, actually, maybe I'll just do it here in R to save time. So let's see. I'm going to again take the weighted average within each node. So it's going to be 7 out of the 10 observations are in that node. So 7/10 times the entropy in that node plus 3/10 times the entropy in the other node. 3/10 times the entropy in the other node. Now, the entropy in this node is 0, right? The entropy for a pure node is 0, so that's not there. That's just 0. So basically, I need 7/10 times the entropy in this node. The entropy in that node is going to be, let's see, negative 4 out of 7 times log of 4/7 divided by log of 2. And then minus, you don't want to mess up the signs here, 3 out of 7 times log of 3/7 divided by log of 2. Right, so it's just p times log of p. Sorry, negative p times log of p. Negative p times log of p. Okay, I think that's right. Did I mess up? So that says it's 0.6897. 0.6897. And so if I take the difference here, 10 minus 7 is 3, 10 minus 9 is 1, 16 minus 8 is 8, 8 minus 6 is 2. 0.2813 should be the info gain, the information gain, when splitting on attribute A. Let me check my notes and also check the question. Is there really an attribute called A? Yes, there is. So when I split on it, the information gain is 0.2813 because I went from my original entropy down to my entropy of 0.6897. So the information gain is 0.2813 for splitting on attribute A for question 38, and that is correct. And if you're curious, if you split on attribute B, the information gain would be 0.2565, which is close, but not as big. So actually, attribute A is the better one, right? Because this is information gain, right? So this is the one with the smaller entropy. And so the entropy when you do B actually comes out bigger, so the information gain when you subtract is smaller. So attribute A in this example gives me the bigger information gain. So C45, for example, would choose to split on attribute A over attribute B in this example when it starts growing the tree. Okay, great. Any questions on that one? Okay, so the last thing to talk about with regard to growing trees then, at least in terms of the criteria for splitting, is what do you do when you have something that's numeric, right? So attribute A3, for example, which is not only numeric but allegedly continuous here, right? Even though it only has one decimal. Okay, so compute the information gain for every possible split. So what you do for this, now I said a lot of algorithms use midpoints, and that's actually what the textbook authors had in mind for this one would be that you would just use the midpoint. So what you actually have to do, I mean, you could do something sort of, an intelligent sort of partitioning or gradient search, but arguably, every partitioning is legitimate, right, that uses a midpoint. So if I were doing this exercise, right, number 39, one thing I could do just sort of for brute force is to go through and write down the possible midpoints, because every midpoint is arguably a candidate for being a split. So I have A3 at 1, and then I have A3 at 3.0. So 2.0 is a split candidate. And then 1, and I have 3.0, and then there's a 4.0. So I ought to entertain the possibility of splitting on 3.5. So all of these are split candidates. And then for each one, I could compute the info gain, right, which would be the original entropy minus the new entropy when you split on that one. Well, let's see. What is the original entropy for this one? Let's see. I can compute that. It should be 1, 2, 3, 4 out of 9. So the original entropy would be the entropy for 4 out of 9 before I do any splitting. So let's see. What's the entropy like for 4 out of 9? It's trying to recycle some stuff here. Entropy, let's try this. I can do the entropy for 4 out of 9 by using this thing here and say it's going to be 4 out of 9 times log of 4 out of 9 minus 5 out of 9 times log of 5 out of 9. So the original entropy looks like 0.9910. If I were, it's always the case, right? 0.9910 is the original entropy. So for all of these, right, I would take the 0.9910 minus whatever. So it doesn't really matter, right? It's not going to affect which one you choose, but technically if someone says, what's the information gain? It's the old entropy minus the new entropy. Okay, so then the other question is, what's the new entropy if I split on 2.0? Well, if I split on 2.0, then I split off exactly one guy, right? And so that one guy, right, is going to be the one guy that's less than 2.0, which has a value of plus, but doesn't really matter. That's going to be a pure node. So it's going to be one of the 9 guys, which has an entropy of 0, because it's going to be a pure node. And then the other 8 out of the 9 guys, I would figure out what is the entropy for them. And so you see for them, let's see. So this guy is gone. So out of the other 8, there's 1, 2, 3 pluses and 5 negatives. So it would be negative 3/8 times log base 2 of 3/8 minus 5/8 times log base 2 of 5/8. And you can kind of see, I mean, you can imagine if you were to make this table, it actually might sort of be instructive to you, because these numbers, these fractions as you go down are going to become more balanced, which is good, right? Because these criteria, they want sort of 2 nodes that are both big and pure, right? So you're going to trade off, this node is pure, but it's not very big. And it would be better if you could sort of get more on both sides, but still keep the purity. So all these criteria are ways of trading off sort of the size of the nodes with the purity within the node. And for that reason, you can imagine why Gini index and entropy might give you different answers. Okay, but in this case, I have one pure node, but it's small. So that's good, but bad. And then sort of this node, which is big, which is good, but not that pure. And let's see, if I were to actually compute this thing, instead of just talking about it, then what would it be? So it would be 0.9910 minus, let's see, oh, I can probably recycle something. Let me recycle this. So 0.9910 minus the entropy in that node times 8, 9. So actually, this should be distribute the negative through, right? Okay, 0.9910 minus the entropy in that node, which should be 8/9 times the entropy in that node, which is negative 3/8 times log of 3/8. Oh, sorry, 3/8 times log of 3/8 minus 5/8 times log of 5/8. That looks right. I think I have my signs right. So 0.1426 would be the information gain there. 1426 is the information gain if you split A3 bigger than 2 or less than 2. Let me just check the thing. What is this, number 39? Yes, 0.1427 I wrote down before. So 0.142 something is the information gain when you split on A3 plus or minus 2. And then you can go through and again, do the information gain for all the other split points, and that will tell you, what the best split point is. And then if you were really growing the tree, you would compare that best split point to the information gain using either A1 or A2. So that's sort of what the tree does. It has to look at every attribute, and for every attribute, it has to look at every split point. But in order to save time, of course, it just does this in this greedy fashion where it doesn't sort of, look ahead or look back, because already there's sort of a lot of computation to do just in this greedy fashion. Okay, so that's number 39. Any questions about that? So if you sort of want to see the solutions for all these, this is one of the homework problems, so they'll be up online. But it's just a case of going through and computing the information gain for every possible split point. Okay, here's a picture, just to show you that they are different. Now, they didn't scale this picture, so that's arguably you should scale it, because misclassification error and Gini max out at 0.5 and entropy maxes out at 1. Arguably, you should scale it, but if you just look at Gini and misclassification error, which are already scaled, you see sort of why they're different, right? Gini sort of has a steeper derivative near 0 and a flatter derivative near 0.5, whereas misclassification error is linear. So the extent to which you value sort of purity for each one of them is different. I mean, they're both monotone, obviously, but this one is steeper here and flatter here, so you can see why Gini index would favor different splits than misclassification error would, and that's the point of showing this picture. Now, you might ask, how in the world did you draw this picture? Because it only depends on P, and I thought there was like a P1 and a P2. Well, of course, P2 is simply 1 minus P1. And so if you look at something like the Gini index, which says it's, Gini index is like 1 minus P1 squared minus P2 squared, well, let's just call P1 P, and let's just call P2 1 minus P, right? Because for the 2-class problem, everything we've been doing has been general enough that we can handle the, K-class problem. But for the 2-class problem, that's all Gini index really is. And so that's 1 minus P squared minus 1 plus 2P minus P squared. So it looks like I lose my 1, but I have a minus 2P squared and plus 2P. So if I factor out the P squared and reorder, factor out the P and reorder, let's factor out the 2 also, then that's just going to be P times 1 minus P, right? P times 1 minus P. So you see that, wait, that's right? Negative 2P squared and positive 2P. Yeah, so you see that this thing here, if you're sort of a stats person, or I guess anyone can see this, that's the binomial variance, right? If you remember from your elementary stat class, you form a confidence interval for the binomial distribution. The variance for binomial is always P times 1 minus P. So that's really what Gini entropy is. So it's probably not a big surprise that statisticians, when they're growing a tree, minimize this type of thing, because it's simply a generalization of the binomial variance. Okay, that's all I wanted to say. Any questions, comments about this picture? Question?
I was curious, is there a case like a Gini index and entropy would lead to like a different split point?
Yes. I think there's an example in the, maybe there's an example of classification error. But yeah, Gini index and entropy can lead to different splits. Yeah.
What's the intuition of that?
So one of them values purity relative to size more than the other. And if you normalize this to be on the same scale, you could see that one of them has more steepness than the other. I mean, the question is like, legitimate people or reasonable people can disagree if I say, okay, I give you 2 nodes of this size and both of them have this much purity, versus I give you 2 nodes of this size and they have this much purity. The question is sort of, is splitting off 3 points with perfect purity, when 3 is a very small number, better than splitting off a lot of points with not so perfect purity? It depends how you measure purity. And if you measure purity differently, then one might favor one over the other. So you can get different answers depending on what you use. And it's not too hard to construct them. Someone had a comment in the back there.
Oh, so is there any case where entropy is better than Gini or vice versa?
I mean, it's hard to say sort of absolute terms, right? I mean, you can sort of motivate both of them. There's some, I can give you statistical arguments for using Gini index. I can give you probably entropy. You can sort of argue it from a maximum likelihood optimality point of view. You can give some optimality arguments for either one, but sort of in practice, you know, some people prefer one over the other. It just happens, I think, that the Gini index was popular in stats and entropy got popular in the CS literature, which led to C4-5. But I don't have the best historical perspective on that. But there's sort of two competing measures, and both of them have strong motivations. But it's, you know, we would not say one is absolutely better than the other. Okay. I mean, you can derive optimality properties for both, depending on how you started things. Okay, any other comments, questions on Gini entropy trade-off? Okay. In general, though, very few people use misclassification error when they're actually fitting these models. They only use it in the end when they want to see how good it did, how well it did. Okay, so the other question from this chapter, of course, is when to stop splitting. This is a tricky question. You know, if there's no answer on what measure to use, there's really no answer on this, because the idea of like how big should you grow the tree, that's really a question of model selection, and it really says, you know, you don't want to overfit, you don't want to underfit, and you know that's a hard thing to do because you never really know whether you're overfitting or underfitting. You know, at best you can leave out some data for testing, but that really depends on what data you leave out for testing, and it's hard to really, you know, compare two trees of similar size. One thing you could do in terms of answering this question of how to grow the tree would be look at your misclassification error, or even if you want your Gini index or your entropy, on the test data, and stop when that begins to increase, right? So start growing the tree, look at your misclassification error on the test data, it's going to go down, 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 but eventually it'll start going up, up, up. So right where it starts to go up, that's it. You should stop growing the tree because you're overfitting. That's one thing people do. Another thing people do, often in conjunction with that, is what's known as pruning, which is, it also gets back to the fact that you're growing the trees suboptimally. So you really want to sort of look ahead one step or two steps. So pruning actually, in some way, looks ahead all the way. Pruning, the idea with pruning is it just basically, it grows the whole tree, right? So your book calls it post-pruning. A large tree is fit. Grow it all the way down. Grow it as large as you want, according to some criterion, maybe Gini index or something like that. And then trim it back, maybe according to a different criterion, maybe even this time measuring the error on the test set as opposed to the training set. So if you look at the documentation for our part, it actually uses pruning like this. It actually grows a large tree and then starts to do some intelligent ways of growing it back. When it grows the large tree, it just minimizes Gini index on the training data. But when it trims it back, it tries to do some more intelligent things with cross-validation and things like that. So you can read the documentation on that. Of course, our part generally is trying to follow the CART algorithm as outlined in the famous text called Classification and Regression Trees from '84. And so when I say these algorithms are old, you know, that's what I mean by old, 1984. But again, they're still used somewhat. They have some nice features. They do nice variable selection, and they're the basis for many other modern algorithms, such as bagging, and people often use these trees for regression or for boosting. Okay, so that's what I wanted to say about pruning. I think that's it. Yeah, question. Yes.
I'm wondering, like, you said use test the data to decide like when to stop.
Right,
about
right.
how big the model should
Right,
be.
right.
Does it like kind of use test data as training data? It's a proof
Yeah,
like a
so,
test data?
so you can, I mean, a lot of problems here, right? If I say, like, I'm going to look at the test data every time and use that as my criterion, then arguably I'm overfitting the test data too, right? Which is one
You
problem.
kind of use test data.
Yeah, I'm using it to decide how big the tree is, so I've already seen it many times, and now I'm cheating again, right? And so, you know, it gets, you're overfitting your test data as well as your training data, right? So, you know, that's why this is sort of a subtle business. And to really know exactly the perfect tree that's going to do the best on the new data, it's really hard to know. And the question is, how efficiently can I use my training data, my test data? I don't want to use the same data more than once, but then if I, you know, split off, if I'm going to consider 10 trees and I split off 10 test sets, then all those test sets are going to be small, and small isn't good either. And it's just, there's no right answer to how to do this. People have their own favorite ways. You know, tenfold cross-validation is very popular, things like that, but there's no sort of right answer to do this. And, you know, in the end of the day, when people have competitions for you know, machine learning problems and they're trying to do a classification task, you don't know if you're going to win the contest, right, before it's over. So there's no sort of right answer to this, but different people have different things they like to do. The one thing you wouldn't want to do is just always believe your training data, because you're always going to overfit your training data. You always can overfit your training data. So you can also overfit your test data. Comment?
What is pre-pruning?
So pre-pruning is just like stopping early. I don't know, the book differentiates pre-pruning and post-pruning and says pre-pruning would be like stop growing at a certain point, which to me isn't really pruning. Pruning is post-pruning to me. I don't know why the authors write that, but they do, and you can see on page 185 they make that distinction. Okay, so I think that's all I wanted to say about this chapter, although one thing that sort of goes along with this chapter, which I don't know why they put it in chapter 5, is to talk about sort of this class imbalance problem. So I'm just going to spend the last 15 minutes here talking about this, which arguably I think should be in chapter 4. So we'll just do it here. So far we've talked about sort of the two classes being equal, right? And by that I mean we've always sort of assumed the same type of loss for both types of errors, right? If it's a rock and I say it's a piece of metal, or if it's a piece of metal and I say it's a rock, I lose $1 either way, right? If a patient is going to die tomorrow and I tell them they're okay, it's the same cost as if they're okay and I tell them they're going to die tomorrow. And you know that's not true, right, in that case. I've always used 50% as the cutoff, right? When I was looking at the probabilities and I said method equal class, its threshold's at 0.5. I always pick the majority of the class in the terminal node, okay? So this is reasonable if the following three things are true, right? First of all, you have to have the same cost for both types of error. You're only interested in the 0.5 cutoff. And the ratio of the two classes in your training data will match that in the population for the most part, meaning that you don't start off with a population that's 30-70 and someone says, here, I'm going to give you 100 of both. Well, if you know the population is 30-70, but the way they sampled the data was to give you 100 of both, then you know that you sort of have to rebalance the things if you want to do the inference on that population. So you sort of need to have all these things true, and in many cases they aren't. And the most striking case is when you're sort of predicting a class that's very rare, right? You're trying to do, find the terrorist in the whole database, or find, the few documents that match this query in the whole corpus of documents out there. So, a lot of times classification is not symmetric at all, and it's very imbalanced. And in that case, misclassification error isn't always what you want to do. You don't always want to train the classifier to have equal cost for both types of errors. So again, if any one of these three conditions is not true, you might want to sort of turn up or turn down the number of observations being classified as positive. So you should think of every classifier as having a knob. And you can either turn it up or turn it down to get more or less of the positive class, okay? This can be done in a number of ways depending on the classifier. Now, some methods give you a probability estimate, right? Logistic regression spits out a probability estimate. CART and RPART, they tell you how many observations are in that terminal node, so you have a local probability estimate. Some don't give you that, right? But some give you some continuous threshold, right? Like for AdaBoost, right? Sometimes people try and use that value that it's computing, that continuous value that's on negative infinity to infinity, and they sort of threshold on that. A lot of things don't really give you a probability, but they give you some sort of ranking of the confidence of, this is the most likely to be the positive class. This is the second most likely. And so you can sort of move your threshold along there. You can sort of turn the knob up and down depending on how many positives you want to get. Over-under sampling kind of works, right? If the classifier has no way to turn the knob at all, you can always trick it. And you can just, give it, repeat the positives twice as many times, or hide some of the negatives from it, or things like that. That's over-under sampling. You can always sort of trick the classifier into seeing more or less of the positive class by controlling how you do the sampling. Okay, so when dealing with class imbalance, you hear a lot of people, they don't really care about, the accuracy or the misclassification error by itself. They would rather look separately at recall and precision. And of course, this comes from information retrieval, and I'm sure everyone in this room has probably heard these terms at some point before. Recall is simply you look at all the ones that are actually of the class you're interested in, and you figure out how many of those you got. Right? So there's all these documents out here that are relevant to that query. How many of them was I actually able to pull up? Okay, that's where this comes from in the information retrieval case. Precision is you look at all the documents that you pulled up, all the ones that you said were yes, and you see how many of them you actually should have pulled up, right? So of all the things you got, how many of them were actually right? Right? So two different questions. Out of all the things that are out there that you should have got, how many did you get? How many did you recall? Versus all the things that you said you thought were the yes class, how many of them actually are? Okay, so of course you can make one of these, one by sacrificing the other, right? I can say, oh, everyone's a terrorist, 100% recall, but low precision. Or I can say, right, you can sort of, do that. That's trivial, right? So this is sort of recall and precision. Before we just looked at accuracy. Now, some people do like to compute recall and precision, but then combine them into a single number. and that single number is called f. Your book calls it f1 because there's sort of a weighting parameter, and 1 is the case where you set them both equal. F is simply the harmonic mean of recall and precision, right? 2 divided by 1 over recall plus 1 over precision. And it turns out actually, the Wikipedia article on information retrieval is pretty good, or else I should say, I know so little about information retrieval that I think that it's a good article. So maybe you can find fault with it. But I thought it looked like a good article, and it talks about recall and precision, even talks about the F measure. And so that's talked about on page 297. The ROC curve is the thing I wanted to talk about specifically, though. This stands for receiver operating characteristic. There's some history about why it has such a funny name. Because you can turn up or turn down any classifier in terms of the positives or negatives, it's really unfair to just compare two classifiers at one point on that dial, right? If I say, let me just compare the two classifiers at the 0.5, at the 50% point, well, one might do better than the other. But what happens then if you pick that classifier, as you turn it up, it might turn out that the other classifier would have done better when you're trying to get a lot more positives out. So you can sort of compare two classifiers simultaneously as you turn up and turn down the knobs by looking at the ROC curve, which is a plot on the y-axis of the total positive rate, and the x-axis has the false positive rate. So sorry, I said total. True positive rate on the y-axis and false positive rate on the x-axis. And you say, well, how does a single classifier give me multiple values for the true positive rate and the false positive rate? Well, you turn up and you turn down the dial, right? As I get more positives, my true positive rate is going to go up, and so is my false positive rate. As I turn it down, they're both going to go down. So what you want, of course, is this to be big and this to be small. There's going to be a trade-off. They don't vary independently. And so you want to take the classifier that sort of consistently does better with respect to both of these as you turn up and turn down the knob, especially if you're going to be using that classifier at different thresholds, right? If you just want one classifier that works at the 0.5 threshold or the 0.7 threshold, okay, you just look at misclassification error and compare that way. But if you want a classifier that works sort of as you turn up and turn down the knob and you want to compare them, the ROC curve is useful for looking at that. So again, true positive rate on the y-axis, false positive on the x-axis. So therefore, the diagonal is sort of as bad as you can do, right? The diagonal would be like a random guess. If I say, let me call everything, I'm going to flip a coin, right? Or 30% of the things I'm going to call positive. Well, then you're going to have a 30% true positive rate and a 30% false positive rate, right? Because everything is going to be 30% positive, right? So you look back at these, right? Everything is going to be 30% positive, so both of these would be 30%. So, anything like that, the diagonal is just simply random guessing. A good classifier is going to be on the upper left, right? Why is that? Because true positive rate on the y-axis, false positive rate on the x-axis. You want this to be low, you want this to be high, so you want to be like up here. Diagonal is random guessing. Okay, so everything should be above the diagonal. If you're below that, you should just flip a coin. A good classifier lies near the upper left. These are useful for comparing two classifiers. The better classifier will be on top more often, right? Sometimes someone will say this classifier completely dominates the other one on the ROC curve, meaning that it's always above it. But if someone just computes with classification error, and so you could just do better at one point. So you like to see if one really dominates the others. If they cross, then it's sort of questionable. Two classifiers that cross, one way you could use this to compare them is to compute the area under the curve, right? The diagonal has area 0.5. Perfect classifier would have area 1. So you could compare the area, under the curve for two different classifiers. And, maybe they cross, but maybe one of them has a bigger area than the other, so you pick the one with the bigger area. So those two classifiers would both be really good, right? But to choose between them, since they cross, I might look at the area under the curve. Okay, so I wanted to sort of get to this example. I only have 7 minutes, but at least maybe I can start it. So this is one of the problems from the textbook. Basically, they're asking you to compare two classifiers. And these two classifiers, M1 and M2, happen to spit out probability estimates, right? This 0.73 means that classifier M1 thinks there's a 73% probability that observation 1 is really from the positive class. And I actually sort of put Bayesian spin on that one, but you understand these to be probability estimates. The point is, though, it actually doesn't matter. All you really need is numbers that you can order these things by. So the 0.73 doesn't matter so much as that that's the largest number. So this observation, if that classifier had to pick just one thing, if you turn down the positive all the way to the point where you're only getting one positive, this is the guy that it's going to say is positive, okay? So whereas over here, 0.68 is the highest, the other classifier M2 would have picked the third observation as being the thing that it thinks most likely is positive, and actually it would have even gotten it wrong. So it might be a bad classifier. So what they're asking you to do here is to make the ROC curve. So what that means is that at every cutoff, you should go through and compute the false positive and false negative rate. So the first thing you just have to do is simply order these things. So this is the instance. And again, let me just do it for classifier M1. Okay, so I'll do M1, let's see, false positive rate, and M1 true positive rate. Okay, so if anything is, so the first one is 1, right, 0.73. Okay, so instance 1 gets classified as positive. So now my false positive rate, well, I haven't said anything, so false positive rate is 0 out of 5, right? Because out of the five negatives, I haven't called any of them positive yet. But the true positive rate, I got one of them right? One of the 5 positives, I got it right, so my true positive rate is 1 out of 5. The next guy, let's see, who's the next guy would be observation 2, right? Because he has 0.69, second highest, so this would be instant 2. So his false positive rate is still 0 out of 5. True positive rate is now 2 out of 5. And you can see that as you plot these, again, false positive rate, true positive rate, let's see. Let me go 0.2, 0.4, 0.6, 0.8, 1.0, 0.2, 0.4, 0.6, 0.8, 1.0, right? Everything's out of 5. So now I'm up to the 0.0, 0.4 with this guy. The next instance would be instance 5, right? 5 has a 0.67, that's the third highest. And again, I got that one right too, that's also positive. So now I'm still a 0 false positive rate, but I'm getting 3 out of 5 on the true positive. I'm now up here. So far my ROC curve is going straight up, which is perfect. However, when I get to the next one, 0.55, that's a negative, I get it wrong. That's a negative, I get it wrong. So that's case 4. So now my false positive rate is 1 out of 5. My true positive rate is still 3 out of 5. So now I start to move horizontally, which is bad, right? Okay, the next case would be number 6, which is a 0.47. 0.47 for number 6. Okay, I get that one right. So my false positive rate stays at 1 out of 5. My true positive rate now goes up to 4 out of 5. So I get to go up again here. The next guy would be observation 9. That's also positive. I get him right because he has probably 0.45. So now my false positive rate stays at 1 out of 5. True positive rate is now at 5 out of 5, right? So now I'm all the way to the top. And then you can imagine after that what's going to happen. You're going to stay at 100%, but as you call more and more things positive, all that's going to happen is that your false positive rate is going to keep going up. So that's the ROC curve for M1. And the exercise asks you to make the same thing for M2. You can see that one actually does pretty well because it shoots straight up, goes over a little bit, but then keeps shooting up. So what you want is you want this thing to get to 1 really fast. You want this thing to get to 1 really slowly. They're both obviously starting at 0. If you don't call anything a positive, they're both 0. But what you want is this one to grow faster than this one because you want to get up fast and over slowly. And so this classifier actually does pretty well. And you can compare M2 on the same thing. And so it's measuring as you turn up the positives, right? As you turn up the positives, how well are you doing? You want to be high and you want to be to the left. And in particular, you want to be above the diagonal. So that's that exercise. And then the last one here says, suppose I choose a cutoff of 0.5. So where was 0.5? 0.5 would be after observation number 4, right? Because my 4 guy was 0.55, but my 6 guy was 0.47. So suppose I choose the cutoff here. Okay, and this was, I think it was plus, negative, right? So suppose I choose it there, then it asks me to compute simply the, give the precision, recall, and F measure. Okay, so precision, recall, and F measure. So precision, well, I've called 4 things positive, right? Because I'm calling all these things positive. 3 out of 4 of them are actually right. So my precision would be 3 out of 4, or 0.75, right? Out of all the things I called positive, well, if I call everything above 0.5 positive, that's these 4. 3 out of 4 of them are right. Recall, well, you know that in the data, there's actually 5 positives out there, right? 1, 2, 3, 4, 5. How many of them did you get? You got 3 of them. So your recall is 3 out of 5, or 60%. Now, of course, that's just the precision and recall for one threshold. You could compute it for all the thresholds, or you could look at the ROC curve for all the thresholds. And the final thing it asks for is the F measure. F measure is just the harmonic mean of these two guys. So that would be 2 times 0.75 times 0.6 over 0.75 plus 0.6. And your F measure comes out to be 0.667. So if you had to report sort of, one number, you had to report your F measure, you would report 0.667. But again, that's just for a single threshold. You can get different recall and precision in F measures depending on as you change the threshold. The ROC curve is nice because it sort of evaluates the classifiers over all possible thresholds. Okay, that's it. Any questions before we take off? Okay, I'll see you on Tuesday.